Hello, ni hao. My name is Robert Traver. I'm the director of the Villanova Center for Resilient Water Systems, and I'm glad to come to your symposium on Sponge City, talking about our lessons we've learned from over 20 years of stormwater infrastructure research. I will say I enjoyed visiting your country a couple times, looking at some of your Sponge City practices, and once as a tourist. And hopefully we can get together in a couple of years at the next symposium and get some PJO together and have some good discussions on stormwater issues and what the things that we're learning. Okay, Sponge City, we have a Sponge City in Philadelphia in the United States. We also call it green infrastructure. And the lessons we have learned is really that Sponge City concept works. Hands down, it works, it's possible. We found that infiltration and evapotration are powerful forces, but we also found it needs to be designed and constructed as a system based upon infiltration and evapotranspiration. And that system must include the design of maintenance. If you don't do that, it's not going to work so well. And also we're finding it can really help with extreme events. A lot of the times in the United States, they kind of think this doesn't help when a large storm hits, but it can. Just to get you a little framework, we're in Philadelphia on the East Coast of the United States. We get about twice the rain that you get in Tianjin, about 1,200 millimeters. And ours is spread out a little bit more during the year, and yours looks like it's a little more focused in July and August as your wet and rainy season. So bear that in mind as we talk about our projects, there are differences in our climate, just as there would be if I was talking to somebody from San Francisco in the United States, from Philadelphia. Our lessons that we've learned are based upon our research and demonstration part. We've been looking at stormwater and green infrastructure for over 20 years. Our wetlands up in the upper left, we first started building it in 1999, the last decade. We also, last century, I guess I should say. The rain garden in the upper right, we'll talk about later, is now 20 years old. And all these systems are operational. And there was the new one on the right that says 2019, that's a brand new dorm complex that our university built rain gardens in as part of that process. We are also doing sites inside Philadelphia. Here's what we call the zoo and rain gardens, because it's next to the zoo, and you can see these two rain gardens are next to a busy Girard Avenue in Philadelphia. And also, it's a little different design. We have a rock bed to the side, which is based upon hitting utilities underneath of it, and they had to move the rock bed, which I'm very happy with. We'll talk about it a little bit later. We're also doing work with the transportation department, rebuilding interstate highway system through Philadelphia, where they're building green infrastructure along the way in this 1700s city block here. So now the residents have a little green space in front of their houses. So what we've learned from this, to design, we need to consider what is our climate, what is our soil properties, and what is your vegetation. Looking at your rainfall patterns, I'd worry about keeping the plants alive in some of the dry seasons. If I look at the configuration of the SCM, or what we call a stormwater control measure, or a rain garden, rain filtration device, the configuration of that is important because it has to be based upon what we just talked about. The runoff capture, how the water gets there, has been more of a problem than we've ever expected. Construction, most of our failures are due to construction. If we don't build it right, it's a problem. And maintenance longevity is a design component we have to consider. Here's a picture from the 1990s of a rain garden. Here's a little more current. This little keep right sign is a little bit more of a joke. I don't know if that's a real sign or not, but it looked funny. So what we've learned about the evolution of infiltration, we now know more about soil physics in stormwater. We know about the vadose, the unsaturated zones, the effect of soil suction and temperature effects on infiltration, the importance of plant available moisture to, one, keep the plants alive so they can build more roots and create pathways to maintain infiltration over the life of a project. Expectations for performance, we now expect some reduction in extreme events. And infiltration is really no longer just a plant science. It's really an engineering science. So we bring in the plant folks, the landscape architects, the geotechnical engineers and the water engineers all together. And in the US, we still have a disconnect between science and practice. A lot of our regulations and design processes are 20 years old. We're not taking advantage of these things. So don't do what we do as we move forward to this. Now we're also learning more about the evolution of evapotranspiration. We realize how important part of it is of a green infrastructure, of splendid city systems, water balance. And we find that evapotration really removes the stored water volume to prepare it for the next storm. So, and that can add reduction. And again, maintain the healthy plant life is so important for maintaining these structures over time. And again, the role of evapotration is supported by science. And again, we still have that same disconnect. One of those interesting plots here is just we have a hanging rain garden in a lysimeter, and we're just measuring the evapotranspiration after a storm. And, you know, if 7 days after a storm, we're getting rid of 30 millimeters of water out of that soil column, that's not too bad. And in our area, we don't have back-to-back storms, so that's not a concern. We have that time. You need time to infiltrate, you need time to evapotranspirate. If we have a permanent water pool at the bottom, you can see we can double that evapotranspiration as it's needed. And I know you know this, I believe this is from Shenzhen, where I was visiting with some good friends there, and one of your, I thought that was a pretty cool green wall. So obviously you understand about evapotranspiration as well. And again, what we kind of found out on these experiments about infiltration and evapotranspiration is you have 7 days, almost no matter what the soil type, it's going to be gone. It's either going to be gone for infiltration or for evapotranspiration. Poor infiltration soils get rid of more by evapotranspiration. Higher infiltration soils have more infiltration and less evapotranspiration. That's important to understand in the design. And then also considering what is the infiltration rate of the in situ soils. That becomes very important as we move forward. So, tell you one story about a site I've talked about in my both previous 2 visits to China. This is a rain garden we built in 2001. We dug it out, mixed soil and media together, and planted it in 2001. And up from that period of time, we are getting different recession rate of the water going into the ground after a rainstorm event. But it's consistent, and we're getting it good performance over the whole period of time, and the performance does not look like it's dropped at all. So that's about 0.5 inches, so about what, 1.25 millimeter. I'm sorry, 1.25 centimeter. All right, or 12.5 millimeters. So I'm messing up my units there. Apologize for that. When I look at this side again, if I just look at the volume in versus volume out, at a certain volume, we have nothing leaving from the storm event. And that's just because the bowl and the soil can store it. I don't have to overflow. If I get some larger events, we do get overflow from the site. However, what struck us is we have a lot of events where we have a lot of volume coming in and the amount leaving is low, much lower than you would expect if I just compared the volume of the storage available. So that clearly told us that we are getting volume infiltration during storm events for these particular storms. And then we had what we call a 200-year, 12-hour storm, it's Hurricane Isaias. And we had a lot of overflow, but we got rid of a good punch of a 200-year, 12-hour storm. So this was, I apologize for the units. So this got rid of a lot of volume, much more than you would expect from a simple rain garden. So it does help in removing the flows from extreme events as well. And the other thing that we found for something like Hurricane Isaias, which is very remarkable, is how fast it was able to empty. It took less than 2 days to empty this site after all that rainfall volume. So then it was ready for the next storm event. That to us is remarkable and a good example of how powerful infiltration is and why we need to consider it as part of reduction for extreme events as well. Another way of looking at it is one nice thing when you've been studying a site for 20 years, you have lots of storm events. This particular site, basically, and I apologize for inches, so that star is about 3.2 inches, which is about what, 30 centimeters, 30 millimeters of water, maybe a little higher, 35 to 40 millimeters of water. So if I take a look, the site was designed for about 25 millimeters. Now that's where that red line is. So all those blue circles are, and the bigger the blue circle means we've had a lot more events of that size. Those represent all the events that nothing left this particular site. The yellow and green are overflow events. The yellow it just barely overflowed, so we're not even sure it really did. The green is it was significant overflow. Doesn't mean it was a lot, but it was significant. It did overflow. And you notice all these blue and yellow circles above my design rainfall of 25 millimeters. All those events are showing there were long drawn out storms that removed a lot of volume that you would not necessarily expect. And I can show lots of storm events like this. Here's another site at the Philadelphia Zoo where we filled it up with 7.6 centimeters one day, had a rainfall overnight of 2.6 centimeters, then another 5.1 centimeters the following day, and it never overflowed. And this site was designed for about 30 millimeters of water. So we had a lot more rainfall than it was designed for. And because it infiltrated continuously through the event, it greatly reduced the impact, even for what I would consider an extreme event. So, practical lessons in design, and this is, I believe, a Xi'an. Basically, took the picture visiting of one of your sites, and we think alike. We have the percent removals based upon volume, sizes, and storms. So, practical lessons in design is first get the water to it. I don't know how many rain gardens I've found that are built that are upstream, and water doesn't flow uphill. We found that design using continuous simulation is much better than design storms. The design storms over-exaggerate the intensity at the center than what we really see. And because of that, they're not really designed right with the ratio of the volume or the infiltration capacities. The incorporation of the designing the soil, so there's enough silts so we can get some vegetation to maintain infiltration pathways, and capturing sediment and trash, we'll talk about in a second. On the configuration of the SCM, do not compact. I don't know how many we found that have failed because of compaction during construction. We are now starting to recommend, if it's designed for 25 millimeters, when it's full, you want to bypass the flows and not divert the flows and not run them through it, causing damage and erosion, because that's going to shorten the lifespan of my SCM. We don't, steep slopes cause erosion, use weirs and break up slopes across rain gardens, we found is good. We highly recommend using what we call a simulated runoff test. Open up the fire hydrants, fill it up and see if it works before you put the media in. That way you know it was built correctly. And anything you do in your design to encourage infiltration. All right, raising outlet orifices, do not having under drains, and then finally inspection and maintenance over time is critical. So here's what I mean about the design storm versus continuous simulation. The blue dots are actual rainfall records of a 3.76 inch rainfall. You can do the math, it's 25 times, that's a lot, about 100 millimeters of water. If it's a design storm using the US standards, a type 2 storm or whatever, we would have a very peak of about 4 times greater than we evidenced during the storm. And we see this over and over and over again. So if we're designing a green infrastructure for a design storm, you're designing for that peak. If you're designing for what really happens, you're designing for the whole infiltration capacity of the storm event. And so one of the ways I kind of look at it is, if my rainfall intensity is higher than my exfiltration, I'm going to need some ponding for a lot of storms for that water to be captured and infiltrated. If it's a really very high intensity and more than I can possibly hold in a pond, I'm going to need a separate facility for flood control. If it's a low intensity, there should be no problem managing this without having a gargantuan storage area, a large storage area above it. And so here's looking back at that bubble chart. If I'm looking up in here, I'm looking at more in higher intensity. If I'm looking below that dashed line, I'm looking at lower intensity. So I can design, so I can get almost anything below that lower intensity and remove it completely. And above that dashed line, I can slow down. I can at least reduce some of the impact, even if I don't eliminate it. Okay, so just to review quickly of the design elements, take advantage of your soil physics and infiltration. Underlying soil, if you have good infiltration capacity in the underlying soil, then that's what you really want, because you can get a lot of performance out of that particular site. Media, when I grow plants, it's really a transmission to my infiltration underneath, and water quality, of course. Storage bowl, we're just going to store the water, so when the inflow is greater than my exfiltration rate into the soil. And larger events, I want to bypass once it's full, because that's going to protect it. Our site that worked for 20 years was built that way. I think that's why it's worked for 20 years. And when you talk about maintenance, people talk about how hard it is to maintain these sites. This poor guy is trying to mow this strip in a shopping mall that's not Sponge City. And that's a 3-foot wide mower on a 2-foot wide median strip. To me, that's a lot more work doing that every week than maintaining a rain garden twice a year. Designing for maintenance from all research, get the water in. Once it gets in, stop erosion. We're getting more problems with erosion within our sites than from the sediment coming off the roadways, as an example in the upper right. If the client can't maintain it, here is a sediment stopping an inflow, can't get into that rain garden. This is again from Zian. I like this basically design that you have for capturing trash. I think it's a great design. If anybody can tell me who manufactures this, I'd like to know. And on the right, I just like that sign. We call it trampling as well. Trampling during maintenance can reduce your infiltration process. We know what will infiltrate, what increases infiltration, what decreases infiltration. Very important aspects of it. And if you have a chance, look at this paper by Lee Ibrahimian and a few others, to include myself. We know maintenance, traffic, and most of these are actually related to construction. Most of the things that reduce saturated hydraulic conductivity. That increases it is to the right. Now, at Villanova, I'm going to conclude here with 2 underperforming SMPs, or Sponge City sites. And what we found is there are 2 very different ones. One on the right, there's a limiting layer. By filling it up with water from the hydrants, it did not infiltrate. By doing that inspection, all we had to do is punch a few holes through that limiting layer. Works fine today. One on the left was caused by construction. Very high, a lot of mulch, it all came down and compressed. We are removing that mulch because everything else underneath is okay, and hopefully that'll be in operation. So we do recommend doing a little forensic investigation. Don't spend all your money trying to rebuild it. You may not have to. All right. And then finally, here's another SRT construction test. By filling up this site from fire hydrants, we're actually able to find construction errors, elevations that were wrong. So I really recommend that as a practice. So what have we learned? Infiltration, when you design it, construct it, maintain it, is robust. You can depend upon it. Evapotration is powerful. It really depends on making sure the vegetation is happy. If your vegetation is happy, you probably have a well-working green Sponge City project. Maintenance is a design element. Trying to get the trash to concentrate, trying to avoid erosion within the system, create some low flow areas, or maybe you can get rid of sediment. All are part of your design. And erosion during extreme events can be worse than any sediment coming off the sites. And oversizing is not always effective. If the water can't get there, it doesn't matter how big you build it. And this is a public relations part. People do not want rain gardens. And it's kind of amusing because all that vegetation doesn't look like it's a very well-maintained yard. So I want to thank PennDOT, the Pennsylvania Growing Greener, USC EPA, and my VUSP partners. For the VUSP partners, I want to recognize the Urban Planning and Design Institute of Shenzhen and all my fabulous grad students. I know my contact information is up on your Congress sites. Do not be afraid to email us if you want to chat about some stormwater, or we're always looking for some good grad students. So you have a great day, and thank you very much for your patience.